In the last video, we concluded that the square root of -1 is not contained in the set of real numbers. And this motivates us to build a larger number system which contains the square root of -1. In this video, we cover the construction of complex numbers which contains the square root of -1. Let us look at the construction of complex numbers a bit more formally. Our objective is clear. We want to extend the set of real numbers such that it contains at the very least square root of negative integers. Hence, let us call the extended system as C. So C denotes the extended number system. And at the very least, we want C to should contain square root of -1. So for convenience, we call the square root of -1 as I, and observe that since I is equal to square root of -1, this implies that I square is equal to -1, which is what we have concluded here. Another visual property we want is that in such an extended system, we are able to define addition and multiplication which are closed. So in particular, we want to combine elements using these operations which should not take us outside the set. Specifically, recall that the set of real numbers have two binary operations, plus and multiplication. We want to extend these operations on our extended number system C. So by extension of a binary operation, we mean that if we restrict ourselves to the set of real numbers, which is a subset of C. So we said that we want to extend real numbers to C, which means that the set of real numbers is a subset of this new set. And now we want to extend the addition and multiplication operations on the real. So by extension, we mean that when we restrict ourselves to just the set of real numbers, which is a subset of this extended set, then we recover back the addition and multiplication operations on the real numbers. That is, whenever we operate on two real numbers, we will always get a real number whether it's an addition or a multiplication. And the identity and the multiplication, the additive identity and the multiplicative identity sort of carry forward in this extended operations over C. So this is roughly our objective while we are constructing the set of complex numbers. So let us look at this visual property a bit more. So there are two operations that we are interested in: multiplication and addition. So let us look at first multiplication and see how the implication of the closure under multiplication, what closure under multiplication actually implies for our set C that we want to construct. So recall just from our previous discussion, recall that I is in C and the set of real numbers is a subset of this extended number system. So, and I is actually the square root of -1, which implies I square is equal to -1. So this is what we concluded. This is our visual property, and the next visual property is the closure under multiplication and addition, where both of these operations are sort of an extension of the operations that we know over real numbers. So first, let us look at the implication of multiplication, the closure of multiplication on this set C that we want to construct. So suppose we start with any B in R. So I'll use this notation for all, which means that you can use any B in this from the set of real numbers. We know that this implies since the real numbers is a subset of this set C that we want to construct, B also belongs to this set C and I belongs to this set C, which implies that B dot I also needs to belong to the set C because we want closure under multiplication. So if you multiply B and I, we want that BI also belongs to the set of to this extended number system C that we want to construct. Now also let's look at the implication of addition. So if we start say with any a comma b, so for all a comma b in the set of real numbers, again from point one, because we want this property, we know that b dot I belongs to C. We just concluded that. So we want b dot I to belong to this extended number system C. Similarly, we want that a plus b times I belongs to C. So we know that since A belongs to the set of real numbers, this A would also belong to the set C, and B dot I, we just saw that it belongs to set C. So their addition should also belong to set C. So in particular, if you have seen the set of complex numbers, this is exactly the set of complex numbers. And what is surprising now is that just looking at these combinations, elements of the form A plus BI, and restricting our extended number system to just these kinds of elements is sufficient. Thus, if we define the set of complex numbers as this set C, which consists of elements of the form a plus bi, where both a and b belong to real numbers, and we define the addition and multiplication operations on them as follows, where addition is simply coordinate-wise addition that we know. So we add the real part and the coefficients for the imaginary part, which is the coefficient of I, the element that gets multiplied with I for each of the elements. And we define multiplication as usual. So think of multiplying two real numbers so the elements are individually addition of two real numbers, and you're multiplying those two elements. So you would sort of open out the bracket with just the simple rule that I square is equal to -1. Then it turns out that this set that we identified, the set of whose elements are of the form a plus bi, where both a and b are in real numbers, and we are calling this set as complex numbers. Then this set is a field under the two operations that we just looked at, the addition and multiplication. So in particular, the complex numbers with addition operation forms an abelian group with 0 as the identity, where 0 is the element from 0 is also the additive identity of real numbers under the addition operation. So, and if we exclude the additive identity, that is 0, from the set of complex numbers, then it forms an abelian group also under the operation of multiplication. So, and the multiplication operation is compatible with the addition operation. That is, the multiplication distributes over the addition operation. And so these are the exact properties of a field, which one can easily check. I've just noted a slightly, maybe a trickier property, that every non-zero element of the form a plus bi has a multiplicative inverse. It looks as follows. So a minus bi upon a square plus b square. So that's the multiplicative inverse of a plus bi. So notice that since it is a non-zero element, both a and b cannot be together 0. And since they are not together 0, that means this is a non-zero element, and hence this element a minus bi divided by a square plus b square is well defined. So in particular, every non-zero element has a multiplicative inverse over C. From a construction, we know that if we look at the subset of complex numbers such that the coefficient of I, which we have denoted as being an arbitrary element, if this coefficient of I is always zero, then we recover the set of real numbers. And moreover, the addition and multiplication on this subset reduces to the ordinary addition and multiplication over the set of real numbers. And both operations are closed. So if we sort of add elements of the form a plus bi, where b is always zero, then we will always get an element whose coefficient of I is zero. Similarly with multiplication. So the additive identity and the multiplicative identity of the complex numbers we noted were 0 and 1, and they both live in this subset. So the most important observation for us is that the set of real numbers is a subset of the set of complex numbers. That is, it sits inside this set C. And the addition and multiplication operation sort of, if you restrict to the set of real numbers, it gets restricted to that subset itself, and its identities are also intact. So the multiplicative identity and the additive identity. So in particular, real number sits inside C as a field with addition, multiplication, and identities all intact. So when a field F is extended to a larger field E, such that the field F sits inside E as a subfield. So in our example, F is the set of real numbers and E is the set of complex numbers. So F is extended to E, so reals was extended to the set of complex numbers, and the reals were sitting inside the complex numbers as a subfield. So meaning the addition and multiplication of the reals, so F in this case, and the identities are all preserved. Then we say E is a field extension of F. So from our construction, we see that C is a field extension of R and R is also a field extension of Q. So complex numbers is a field extension of real numbers and real numbers is a field extension of the set of rational numbers. Finally, we arrive at the theorem that tells us that the construction of our number system is complete. In particular, remember that we always constructed a bigger number system because there were polynomial equations that did not have solution within the existing number system. So in particular, Gauss did not just define complex numbers, he resolved an important question. This result, which is known as the fundamental theorem of algebra, can be used to conclude that every polynomial equation over the set of complex numbers has all its solutions in the set of complex numbers itself. This essentially means we do not have to create a larger number system. The fundamental theorem of algebra states that a polynomial over complex numbers has a linear factor over the set of complex numbers itself. So polynomials are objects of the form a0 plus a1x plus dot 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 a d x power d, where d is an arbitrary natural number. So you could like have d equal to 1 or d equal to 5 and so on. And the elements of this form, all the elements of this form together form the set of polynomials where x is an indeterminate. So when you define a polynomial, x is an indeterminate and its coefficients always come from a field. So in our case, the coefficients are coming from the set of complex numbers. So we say that we use this to denote the set of polynomials of over complex numbers where the coefficients are essentially coming from the set of complex numbers. So A naught to AD here is in the set of complex numbers, and D is an arbitrary natural number. A linear factor or a linear polynomial is just an element from this set, the set of polynomials over the field of complex numbers that has degree 1. So a linear factor always has degree 1. So they are elements of the form a0 plus a1 times x. The fundamental theorem of algebra implies that p of x, if say p of x is a degree d polynomial, it has a linear factor of the form say a0 plus a1x. And having a linear factor implies that there is a polynomial q of x of degree d minus 1, such that p of x can be written as a0 plus a1x times q of x. This is because so a factor means that the linear it divides p of x completely. So when you divide, there'll be no remainder, and so you can sort of write this expression where p of x is a0 plus a1 times multiplied by q of x, where the degree of q of x is d minus 1 exactly, assuming that p of x is a degree d polynomial. So now we can normalize, we can sort of pull a1 out common, and we can write this as just say r plus x times q of x, or let me just put minus r. So r is minus of a1 minus of a naught by a1. So in general, we sort of, so you can sort of push this A1 now into Q of X, and this starts looking like A1 times Q of X, which is again a degree D minus 1 polynomial times X minus R. So in general, we sort of skip this like this normalizing, and we just say that P of X, if it has a linear factor, then there is a polynomial Q of X such that X minus R times Q of X is equal to P of X, where the degree of Q of X is D minus 1. So if you sort of didn't follow this part, then just believe that if there is a linear factor, then it can be written as x minus r, where r is again coming from the field, so it's a complex number, and x minus r divides p of x implies that there is a polynomial q of x of degree 1 smaller than p, so x minus r times q of x is equal to p of x. So if a polynomial can have, if every degree t polynomial can sort of be factored as p of x equal to x minus say r1 times q of x, where q of x is of degree d minus 1. So p is of degree d, q of x is of degree d minus 1. So now I can repeat this. I can repeat this process with q of x, and I can keep going. So I can write in turn p of x as x minus r1 times x minus r2 times say q2 of x, where q2 is now of degree d minus 2. So what I did with p of x, I can repeat with q of x and write it as x minus r2 times q2x. And you can see that I can now just create a bunch of linear factors where p of x is just like product of linear factors. So essentially what fundamental theorem of algebra implies that a polynomial over complex numbers factors like can completely be factorized into linear factors over the set of complex numbers, And this inadvertently means that all of its roots are already in the set of complex numbers and there is nothing left to solve. So in particular, you can see that if p of x is written as x minus r1 times q of x, then r1 is a root. So if I put r1 x equal to r1, I saw say put x equal to r1 in this expression. So p of r1 is equal to 0, which implies that R1 is a solution to this polynomial P of x and implying that R1 is a root. And so since all the factors are, since P of x can be sort of written completely broken down into linear factors, all of its, all the linear factors would eventually give you roots. And it can be shown that all the roots of p of x, so p of x cannot have more than say d roots. So since all these can be written as product of linear factors, all of them sort of belong to C. So this is what it means for the set of complex numbers to be algebraically closed. So no polynomial equation would ever force us to build a larger system, so this tower is complete. So if sort of you did not follow this product of linear factors and how they are sort of turning into roots, it is the takeaway for you. The takeaway would be that complex numbers. So if you take the any polynomial over the set of complex numbers, all its roots belong to the set of complex numbers itself. So you don't have to go and find a larger number system where to determine its roots. So that's essentially what the fundamental theorem of algebra gives us. A full proof of this theorem requires tools from complex analysis, in particular an understanding of how polynomials behave as functions over the set of complex numbers. For now, we state it as a fact and conclude that the number system we have been building, equation by equation, terminates here. In the next video, we will finally see how the cardinality of the set of rational numbers and the set of real numbers compares to the set of natural numbers.